We've now seen that we don't actually have to draw Pascal's triangle to get those binomial coefficients. They are in fact the same as what we saw with combinations. So a reminder, nck, n factorial, k factorial, n minus k factorial. We're going to prove it. We're going to prove it via induction. But the first case will actually be k equals 0 for this one, because nc0 is our first one. So proof for k equals 0. So the left hand side, nc0 is 1. Right hand side, n factorial on 0 factorial, n factorial, also turns out to be 1. So yes indeed, it works for k equals 0. Assume the result's true for, well, I'm going to use k equals r, where r is some integer. So in other words, we're going to assume NCR is n factorial on r factorial, n minus r factorial. We're now going to prove it true for r plus 1. So I want to prove NCR plus 1 is n factorial on r plus 1 factorial, n minus r minus 1 factorial. Okay, here we go. Remember, we know this rule. That came from how do we create Pascal's triangle? We go to the row above and add the two together. So I know that n plus 1 CR plus 1 would be NCR plus NCR plus 1. Rearranging that, NCR plus 1, I've got n plus 1 CR plus 1 minus NCR. Well, my assumption, I'll just substrate in for my assumption. NCR, n factorial, r factorial, n minus r factorial. Now, n and r, n plus 1, r plus 1, it's the same assumption. So n plus 1 factorial, r plus 1 factorial, n minus r factorial. Okay. It's just that instead of n, I've got n plus 1. Playing with that, we get a common denominator, r plus 1 factorial, n minus r factorial. Eventually, n plus 1 minus r minus 1. N minus r cancels with the n minus r factorial. And we have n factorial on r plus 1 factorial, n minus r minus 1 factorial. And I think that was what we were trying to prove. So there we go. So hence true for r plus 1, if it's also true for r. Hence true for all positive integral values by induction. We know it's, when we expand out 1 plus x to the power of n, the binomial coefficients go nc0, nc1, nc2, and so on and so on. We can now write this in some notation. The general term would be nck x to the power of k, and we're going from k equals 0 to n. And nck is as we have defined it. Remember, there will always be one more term than the power when you expand out. So when you expand out the perfect square, you end up with 3 terms, for instance. It tends to be more useful with a and b. So the only difference there is, instead of x to the power of k, I've got b to the power of k, but also a to the power of n minus k. The two powers have to add up to be n. Okay, evaluate 11C4, but oh no, we've lost our calculator. So we have to go back to our definition. 11 factorial on 4 factorial, 7 factorial. That cancels. The 7 factorial would go into the 11 factorial, leaving me with 11 times 10 times 9 times 8 over 4 times 3 times 2 times 1. But now we can have some fun doing some cancelling. 4 2s are 8. And then 3 will go into 9 3 times. 11 times 10 times 3, 330. We're going to find the value of n such that nc5 is equal to nc8. So that's using our relationship about the symmetry. Well, what I know is nck is equal to nc n minus k. So I can say 8 is n minus 5, or another way of thinking about it is, oh well, these two numbers should add up to be n because of the symmetry of the Pascal's triangle. Either way, 8 and 5 is 13. We must be talking about the 13th row. Now, if nc7 plus nc8 is 20c8, now we're talking about that one that says in order to create, we go to the row above. So that one, n minus 1 ck plus n minus 1 ck minus 1 is in ck. So if we want 20 C8, it must have come from the 19th row to work that out. So we know n is 19. If we have to find the 5th term in the expansion, now the order here now becomes important. So 5a is the first term, so we assume we are going to start with 5a to the power of 11 and work our way down that way. So it'd be 5th when we're going in that order. The general term becomes 11 ck minus 3 on b will be to the power of k, which means 5a is to the power of 11 minus k. Notice that's term k plus 1, because the first term would be when k is equal to 0. So I always label it term k plus 1. We want the 5th term, so that'll be on our one when k is 4. So if I substitute 4 in for k, we get our 5th term, 11c4, 5 to the power of 7, negative 3 to the power of 4. Sometimes we leave them unsimplified. That would be an unsimplified answer. It's really big. This is similar to that question this morning. But so the way I did it was informally, but really what I was doing is I was looking at the general term and saying, well, when are the powers going to end up being x to the power of 0? So there's my general term, and 9ck, the 3x squared will be to the power of 9 minus k, the minus 1 on 2x to the power of k. But I'm only interested with x to the power of for now to work out what k is. So x squared to the power of 9 minus k, x to the negative 1 to the power of k will be x to the power of 0. Playing with our index laws, we end up with k being 6. So we now know it's the 7th term. So subbing that back in, and there's the unsimplified answer, 9c6, 3 cubed over 2 to the power of 6. Okay, 5D.